Hi mathematicians, I'm Amy and I'd like to talk to you about some common sense calculus ways for you to identify your trig ratios based on your unit circle. So in my previous video we talked about how to identify all of the angle locations around the unit circle in terms of radians. Now what we're going to do is figure out what all of the coordinates are for each of these points around the circle, and those coordinates will help us figure out our trig ratios. First important thing to keep in mind is that since this is a unit circle, what we know is that the radius all the way around is 1 unit. Let's start by looking at the coordinates for the angle measure for pi over 4. So on this page here, I've highlighted where pi over 4 is. That's this angle here. That angle is pi over 4. And again, we just talked about that the radius, which would be the hypotenuse of this triangle I've just created, the radius here is 1. And so in order to figure out the coordinates for this point here on the circle, assuming that this point here is the origin, 0, 0, we need to find out the length of this side and the length of this side. You might already know how to do that, but I want to do a quick reminder for you on how to figure out what those lengths are. So if I had a 45, 45, and 90 triangle, what I happen to know is that because these angles are congruent, then these two leg sides are also congruent to each other. Remember, we knew that this hypotenuse side was 1. And if you forgot what the lengths of these other two sides are, we can just call them x and use our good friend the Pythagorean theorem to remind ourselves what those lengths are. So of course the Pythagorean theorem is side squared plus side squared equals hypotenuse squared. So we've got x squared plus x squared is 1 squared. That gives us 2x squareds equal to 1. And x squared is equal to 1/2. And of course, when you square root each side of that, so square root x squared, I have x. Square root the other side, now I've introduced the square root, so I have to introduce a plus or minus, and that's plus or minus the square root of 1/2. Now, since we're talking about the length of the side of a triangle, the negative doesn't really make a whole lot of sense here. So what I know is each side is the square root of 1/2. And by the way, remember square root of 1/2 is the square root of 1 over the square root of 2, and the square root of 1 is just 1. So I could express that as 1 over the square root of 2. And I also could rationalize that, as a lot of us have learned to do in prior math classes. So I can multiply top and bottom by root 2 over root 2. Of course, that's equivalent to 1, so I'm changing the look, but not the value. And when I multiply this out, I get root 2 on top, and root 2 times root 2 is 2 on the bottom. So either of these are acceptable expressions for the length of the side. And again, this side here is either 1 over root 2 or root 2 over 2. So when we go back to our unit circle, remember, our hypotenuse is 1, and this side, and of course since we're in quadrant 1 over here, they're both positive values. The x and the y coordinates are both positive. So I have root 2 over 2, comma, root 2 over 2. It's not incorrect, like I said before, to also express that as 1 over root 2, comma, 1 over root 2. In calculus, we're not quite as picky about how you express those values. So either way is just fine. So as you go around the circle, looking at the other 45, 45, 90 triangles that will occur. So here I had pi over 4, 2 pi over 4. So this guy here, remember, is 3 pi over 4. And I haven't drawn in the triangle, but you can kind of imagine, oh, there it is right there. Again, the hypotenuse is 1, so I've got the over and the up, which gives me the coordinates for this point to be negative and then positive. So negative root 2 over 2, comma, positive root 2 over 2. And you can work your way around to the other 45, 45, 90 triangles. I've got one here. So if that's 3 pi over 4, 4 pi over 4, we're here at 5 pi over 4, and I see the x and y coordinates are both negative here, so negative root 2 over 2, comma, negative root 2 over 2. And finally, 6 pi over 4, this guy here is 7 pi over 4. Oops, this guy here is 7 pi over 4. There's your right triangle. Hypotenuse is 1, so over and down, I've got positive and then negative. 2 over 2. There we go. So next let's look at the multiples of pi over 6 and pi over 3 and the coordinates that are associated with those angles on the circle. So here I have a right triangle that's associated with the angle pi over 6. And once again, our hypotenuse length is 1. Remember, pi over 6 is equivalent to 30 degrees. So this is a 30, 60, 90 triangle. When we get to pi over 3, in a minute, the angle here, pi over 3, that angle pi over 3 is the same as 60 degrees. So this guy is actually a 30, 60, 90 triangle as well. It's just orientated a little bit differently. So I always recommend, if you're having trouble with the 30, 60, 90 triangles and which length is what, start with an equilateral triangle. Start with a 60, 60, 60 equilateral triangle. And remember, since the hypotenuse of the triangles on the unit circle, which is the same as the radius of the unit circle, is 1, let's just make each of these sides equivalent to 1. This side here is 1 as well. So what I suggest you do is imagine taking this equilateral triangle and just slicing it in half. And let's do it this way. Just cut it right in half. And I'll put a right angle there, there's a right angle there. So now I've split it into two 30, 60, 90 triangles where this angle here is 30 and this angle here is 30. So there's a 30, 60, 90 and a 30, 60, 90. Oops, 30, 60, 90. All right, so let's figure out what the sides are in each of those. So it turns out, since I cut this perfectly in half, I bisected the angle, therefore bisecting the triangle, we bisected this leg. So this side right here is 1/2 of a unit long, so is this side here. All right, so a half and a half makes a whole, great. So now what we really need to figure out is what is this side here? Remember, the hypotenuse is the longest side. And I'd like for you to remember that the 1/2 is the shortest side. So this other leg, what's the length of that side? And once again, we can use the Pythagorean theorem. We can call that side x to figure out what that length is. So we can say x squared plus 1/2 squared is equal to 1 squared. So we've got x squared plus, and a half squared is just 1 squared over 2 squared, or 1/4, and that all equals 1. So I know that x squared is equal to 3/4, right? I took 1, which is 4/4, I've subtracted a 1/4, I'm left with 3/4. And when I square root each side, of course, I need to include the plus or minus, which gives me plus or minus square root of 3 over, and of course the square root of 4 is 2. Remember, since we're talking about a length on this particular triangle, that's a length, it's going to be a positive value, so we're just going to stick with positive root 3 over 2. So this side right here, square root of 3 over 2. Let's go back to our unit circle and apply these values. All right. So on our pi over 6 triangle, so this, remember, this angle here is the pi over 6. That's the 30 degrees. There's your 60. There's your 90. Remember, we cut that 60, 60, 60 triangle in half. So you can kind of imagine, here's the rest of the triangle here. You kind of envision that was your 60, 60, 60 triangle. Smashed it in half. So this is now our 30-degree angle. Here's our 60-degree angle. So this one, of course, this side here was 1. This side here was 1. So that clearly is the side that was a half, leaving this length here to be our root 3 over 2. Again, the shorter of the two legs is always a half. The other leg is the root 3 over 2. And the hypotenuse is always 1. So as we go around our unit circle here, remember for pi over 6, over and up, those are both positive values. So we're going to say root 3 over 2, comma, 1/2. Now I'm going to go over to this guy over here, which of course is 5 pi over 6, right? This angle here, 5 pi over 6, and I'm going to just sketch in the triangle there, little right triangle. So again, the angle from 0 all the way around here, all the way around to here, gives us 5 pi over 6, but I'm going to be looking at this little triangle here. And again, we've got a 30-degree angle in here, 60 degree and 90. Hopefully you recognize once again that this side is the 1/2 and this side is the root 3 over 2. So as we're naming the coordinates, it's backwards and up. So negative root 3 over 2 and positive 1/2. And of course, down here at, not a perfect drawing, but you get the idea. Down here at, let's see, 6 pi over 6, so that makes this 7 pi over 6. I'm over and down. Oopsie, so negative root 3 over 2 and negative 1/2. And then finally all the way over here at 11 pi over 6, over and down. So we've got positive root 3 over 2 and negative 1/2. Next, let's look at the rest of the 30, 60, 90 triangles. This is the one affiliated with pi over 3, and I have the others that are all sort of orientated similarly. So again, this is our 60-degree angle, this is our 30 up here, and 90. I know the hypotenuse is 1. I know that when I take the equilateral triangle, which would have been, I guess, out here, and cut it in half, this is the side here that ends up being 1/2 a unit long. And this length here is my root 3 over 2. So as we go around for each of these, I'm going to have the x-coordinate be positive 1/2, and the y-coordinate here will be positive root 3 over 2. For 2 pi over 3, which is the angle that comes all the way around to here, but yet the triangle is this one here, this angle here still is 60 degrees, and so I've got 1/2 here, and again root 3 over 2, but as I write them as coordinates, I've got negative and positive. For 4 pi over 3, both coordinates are negative. And for 5 pi over 3, I've got positive and then negative. Now it's important to remember for every one of the right triangles that you can sketch around the unit circle, the hypotenuse is always 1. The adjacent side, here's the angle here, the side that's adjacent to that key angle is going to be your x component, so I'll write adjacent there. And then the vertical distance that's across from your angle, that's going to be considered your opposite side. So when you're coming up with your trig ratios, for instance, if I wanted the sine of pi over 3, sine is opposite over hypotenuse, which is root 3 over 2 over 1. Now it turns out for sine and cosine, since they're both, sine is opposite over hypotenuse and cosine is adjacent over hypotenuse, since they're over 1, the hypotenuse is 1, then really we can consider the sine to just be the y component. The y is equivalent to that opposite side. So really in the unit circle, the y component gives you the sine of the angle. And likewise, the x component is the adjacent side, and that'll give you the cosine of that given angle. So here I have the whole thing filled in. So if I, for instance, wanted to know the cosine of 5 pi over 6, well, I know the cosine is affiliated with the adjacent side, which is the x value, and I have a little handy little reminder here. So the x, y, that's adjacent, opposite, that's cosine, comma, sine. So if I wanted cosine of 5 pi over 6, I know that that's negative root 3 over 2. And if I was stuck on a desert island somewhere and I needed to know the sine of 4 pi over 3, I can take a stick and some dirt. I can sketch a circle, and I can say, okay, 4 pi over 3. Let's see, 1 pi over 3, 2 pi over 3, 3 pi over 3. Oh yeah, 4 pi over 3. That would be here. 4 pi over 3 is the full angle, and I know that this side is 1, I know this side is a half, I know this side is root 3 over 2, so I'm over and down, and I can figure out that the cosine of 4 pi over 3 is negative a half, and I know the sine of 4 pi over 3 is negative root 3 over 2. What if I wanted the tangent of 4 pi over 3, for instance? Well, I know tangent is sine over cosine, or opposite over adjacent. So I just have my opposite side, which is my y component, over my adjacent side. All right, and I can clearly see that this is equal to positive root 3, but if you weren't so sure, you can think, okay, negative over negative is positive, and I have two fractions dividing. I have a fraction divided by another fraction, so I have root 3 over 2 divided by a half. We can flip that guy and multiply, and it turns out that the 2's reduce, and I'm left with positive root 3. So for any of your trig ratios, sine, cosine, tangent, cotangent, cosecant, secant, whatever you got, you can use your unit circle to figure out what the trig ratio is equivalent to. Now, I haven't addressed the north, south, east, or west points on here. Remember that, for instance, for 0 or 2 pi radians, it's hard to draw a triangle, but I know the coordinates here. Coordinates here are 1, 0. The coordinates up here are 0, 1. The coordinates over here are negative 1, 0, and the coordinates down here are 0, negative 1. As long as I can name the coordinates, I can figure out the trig ratios there. For instance, 3 pi over 2, I know the cosine is 0, and I know the sine is negative 1. For 3 pi over 2, if I wanted the tangent, let's see, tangent is sine over cosine, or opposite over adjacent. Negative 1 over 0, undefined. So the tangent at 3 pi over 2 would be undefined. What I recommend you do is print out a blank copy of the unit circle reference page from my website and practice not only your radian measures, but also the coordinates all the way around. This is something you should be able to do. If not from memory, you should be able to recreate fairly quickly by doing a quick sketch. I think you can do it. See you at the next video.